So my talk is going to be a little bit, very different from what we heard so far. It's going to be a little bit technical, and the idea is to slow down a little bit and see what the choice that we make for protocols can be important for the messages that we are getting after having done this, after having analyzed the simulation. And I have to say, I really liked Heian talks yesterday, because it was a great talk to think about stuff, and also the remarks from Paco saying that sometimes it's good to show nasty stuff that we are having in models. On the other hand, I'm really happy as well that we go in this workshop up to the users, because this is where we are ultimately here. And so this is a nice combination to have the two of that. So I'm going to do some introduction about the Pacemaker experiments. So I've tried to make some targeted simulations for this workshop, because we had a lot of thoughts about these component C experiments, where we spent a lot of energy with Wim and Gökhan about thinking about these experiments. And so I did some targeted experiments about this protocol that we may want to choose. So just so the overall goal of this talk would be to provide some analysis to help to choose objectively the restoring parameters that we are using in Pacemaker experiments. Just remember some general sentences about Pacemaker experiments. So the goal of these experiments is to constrain the internal to decadal modes of variability in a couple model to follow the observed fluctuations. And the goal of these experiments is to investigate both the local response to the constrained temporal evolution of the SST modes that we're restoring to, and also the remote ocean atmosphere response in the other basins, oceanic basins, that are basically not constrained and free to revolve, freely coupled. So in principle, this is kind of easy. You add the restoring term of a selected regional domain, you set a buffer zone, and the rest of the system is coupled. But practically, it's not that easy. And we need to be very cautious with this restoring term, because it may create energy imbalance, leading to kind of spin up of the coupled ocean model that is free. And also the restoring term may perturb the local ocean dynamics that can remotely affect the entire system. So we need to find a set of experiments that perturb at the least the equilibrium and the intrinsic physics of the coupled model, while we control the temporal evolution, the low frequency evolution of the SST. So the flux correction that we are adding, the restoring term, the restoring term, sorry, is not a flux correction to correct biases. It's really just to follow the observed fluctuations. So, oops, it's kind of strange. So the usual way we do it, I have this equation. There's a pointer somewhere. Where is it? This guy? How does it work? I don't know how it works. The button? Ah, here it is. So here there's an equation. So usually what we do for this restoring term, we had a term in the flux, in the non-solar flux at the surface. So the non-solar flux at the surface is the one that is computed by the model plus this restoring term, which is called also the feedback coefficient, which is dq dt here. So the unit is in watt per meter square per Kelvin. And so you add this restoring term, this feedback coefficient to the non-solar flux, and then you integrate the model, so the choice of this feedback coefficient is critical. You can do also some restoring in the freshwater flux with the same idea, but I'm not going to talk about this today. I'm going only to talk about this one here, this parameter here. So what I did for this workshop, so I did not have a lot of time and a lot of computer power, so I did simulations, only 20-year simulation with different value of this flux correction term. So using our local model, which is a CNM CM5 model. So I did 3 members from 1986 to 2005 with restoring over the North Atlantic basin, so from 5 degree north to, or 0 degree north to 60 degree north with 10 degree buffer zone, and no restoring under sea ice. So 3 members with a very strong restoring, which is about 2 days, with this 960 watt per meter square per Kelvin correspond to a restoring of 2 days of the SST anomalies with a mixed layer depth equal to 50 meter. I did a weak restoring with 40 watt per meter square per Kelvin, which corresponds to 2 month restoring, and some simulation in between. So I have 3 members for the 2 extremes, only 1 member for this one here. So I'm not talking, not going to do real science with that, because obviously there is not enough member to do science, but I just want to show the impact of this parameter in this realm.
Anything on salinity?
So I haven't done anything on salinity, just adding this term here. And I've done also the same thing for the E-specific pacemaker, so following the paper from Kosaka and Xie in 2013. And I have only 1 member for each restoring parameter. So let's start with the Atlantic experiment. So I'm just showing here the 2 maps of the 2 leading EOF of the SST in winter over this period here in 1986-2005, actually, it's not 12, 20 years. So it's 2 leading mode with so you recognize the traditional tripole and this monopole here, the SST. And here is the time series associated with this mode. So in color, this is the observed time series, so you can really see the shift in 95, 96 with warming after 95, 96, I mean corresponding to this pattern here. And each line here corresponds to the pacemaker experiments that I just described. So in red, this is the one with a very strong restoring. So there are 3 members here. So actually you don't see the 3 members because the restoring is really strong and it's extremely close to the observed pattern. The correlation between the observed curve and the observed time series and the pacemaker time series is 0.99, of course, because the restoring is very strong, is 2 days. And I'm not sure you can see the green and the orange, but they are here, and the correlation is quite high, and the correlation, of course, is decreasing with the restoring diminishing. And for this weak restoring, about 2 months, the correlation is it's still very high. It's around 0.8, and the ensemble mean of this correlation in 8.87. So with this weak restoring, I mean, the internal variability is less constrained, so you see a little bit of noise here. But the decadal variability is very much constrained because the restoring is 2 months. And this is what is expected, actually. For the second EUF, this is about the same thing. The restoring and the correlation is a little bit lower because there's less of variability, but this is the same type of signal that you get. So this is for winter. This is for summer, where in this case, because the mixed layer is very shallow, the restoring actually is very strong, even for 40 watt per meter square per Kelvin. So the constraint, it's strong, and you can really see the shift, and all the pacemaker simulation, they do a good job with this SST, and about the same here. So stronger constraint in winter, I mean, because we choose this fixed parameter of restoring through the season, so the constraint is different in the season because of the seasonal cycle of the mixed layer depth. But what you basically see here is whatever the constraint, the low frequency is very much respected. This is what we want. We want this in the pacemaker experiment. So now let's go a little bit more into detail in the impact of the different restoring in the change in the circulation associated with this, so the restoring term that we are putting. So there are 4 maps here corresponding to the difference. This is barotropic stream function over the Atlantic. So the mean barotropic stream function of the model is shown here, and is for the historical simulation. And in color here, this is the difference between the circulation in the Pacemaker experiment and the historical simulation, without restoring at all. So what we don't want to have change in the mean circulation of the model because because of the restoring. We just want to have the observed fluctuation, which is in the model, but we don't want to change the mean of adding this term. So when you don't see any color, it means that the mean is not changed. So the weak restoring is here at the top, and the very strong restoring 2 days is here at the bottom. So let's start with this one here. With a very strong restoring, actually what happens is you change the circulation of the deep ocean, of the ocean in the Atlantic. So basically what you do, you accelerate very much the subpolar gyre by about 6 to 7 thirds rep, which is about 25% of the mean. And you also accelerate here the subtropical gyre. And you can see from this weak restoring here, there is no change. And it's starting a little bit here with this 10-day restoring, and 2 days restoring, you do like a massive change in the circulation. If you look at the mixed layer depth, so this is in yellow, I'm not sure you can really see. So yellow means increase of mixed layer depth. So what you see for the weak restoring, you have a weak increase of the mixed layer depth in this area here. No change in the circulation, but a weak increase here, which is not that significant. And then progressively, the mixed layer depth plunges with the restoring. And for this one here, there's something very bizarre happening in the subpolar gyre. A very strong increase of the mixed layer depth here along the current, and a decrease of the mixed layer depth in the center. Basically, your dynamics here is completely screwed up. What is happening here, you're advecting a lot of, because the circulation is increased, a lot of salty water is advected here and makes the mixed layer depth very strong. And the fresh water that was stored in this area in the Labrador Sea is confined in the center of the Labrador Sea and cut the convection, which is completely unrealistic here. So you have a very good constraint, of course, at the surface, but the ocean, the circulation of the ocean is very perturbed in that case. So this very strong constraint doesn't work anymore. Okay, this very strong constraint perturb the entire dynamics of the model. So what's going on in terms of AMOC, in terms of AMOC? So in shading here, this is the AMOC variability of the historical simulation, so 10 members. And what you want by restoring the observed fluctuation of the SST, you don't want to change the mean state of the AMOC. You just want to phase the evolution of the AMOC. So the three blue curves here correspond to the AMOC with the weak restoring, and the red curves correspond to the AMOC with a very strong restoring. So basically, what you do with very strong restoring, you accelerate all the circulation, the horizontal circulation and also the meridional circulation, and you have very strong heat transport going on in the ocean up to the north because of this very strong restoring. And you see a kind of progressive increase of the AMOC in the model with the time scale. So you can say, I mean, who cares about that? Because the model atmosphere is going to see only the SST. But the thing is, because we are in a copper system and the rest of the ocean, oh, thank you. Doesn't work.
If you press the right button, it will work.
The large one, nope.
Yeah, it works.
It works? It works on the dark, but it's not. Oh, okay. It doesn't work very much. Sorry, the intent was good. So, yes, I mean, who cares? Actually, this kind of spurious effect is very important because we are in regional coupling. So what I'm showing here is the heat content is the North Tropical Atlantic on the left side, and the heat content in the South Tropical Atlantic on the right side, for the different sets pacemaker experiment. And you can really see that because the MOC is accelerating and the horizontal circulation is also accelerating, the heat content in the North Tropical Atlantic is decreasing. And the interesting thing also, even if in that case the surface temperature is controlled because of the restoring, but in South Tropical Atlantic it's not controlled at all. And the heat content is also decreasing because you're accelerating all this anti-meridional circulation. So the temperature anomalies in the southern North Atlantic, but then you affect the entire system. And these runs were only 20 years long, but if we run them for 100 years, it's going to affect the entire Austral Ocean and then the entire equilibrium in the, of the model. So it's starting a little bit, I can see some signal with a strong restoring in the ACC. It's not significant, but I can really start seeing things propagating in the ACC. So the goal of this is just to be very careful on this with this parameter. One thing which is also very interesting with this, I think this set of simulation is to investigate the relationship between the SST and the atmosphere at very high frequency. High frequency meaning daily frequency. So I'm showing you here a lead-lag correlation between SST and atmospheric field in the model. So basically, let's start with, so this is over the North Tropical Atlantic, and so let's start with the precipitation. So on this side, the ocean leads, and on this side, the atmospheric leads. So basically, what we see is when the SST is warm at lag 0, it is preceded by, so the different curve corresponds to the different pacemaker experiments listed there, and the historical simulation with no restoring is in black. So the historical simulation, if the model is perfect, is like the observation, let's say. So in that case, so you see that when the SST is warm at lag 0, it is preceded by reduced precipitation and followed by increased precipitation. And if you look at the solar heat flux, it is preceded by increased solar heat flux just about 10 days before and decreased solar heat flux 10 days after. Meaning that the SST change at lag 0 here is explained, is a response to the atmosphere. Less solar income leading to warmer SST, and then the atmosphere responds to this warmer SST with clouds and precipitation. So what you see, and this is latent heat on this part here. So what you see with different curves, I mean, we don't want to perturb too much this relationship with the pacemaker experiment, because this is what's going on in nature. So what you see with different curves, that when the restoring is really strong, basically you completely perturb the physical relationship between the ocean and the atmosphere at this time scale. And with a very weak restoring, you closer to the real system, I mean to the reality, which is assessed here by the historical experiment. And this is about the same for all the quantities. So this was for the tropical Atlantic, but the same thing happened with the subpologii. And we know that, let's take only this guy. This is the sea level pressure. When the temperature anomalies over the subpologii, this is in winter, is warm, it is preceded by anticyclonic circulation. 2 minutes? Ouch. It is preceded by anticyclonic circulation, meaning that the ocean is responding to the atmosphere. And this is completely not respected when the restoring is really strong. And it's pretty good when the restoring is really weak. So I'm going to skip this one. I can talk about this later if I have questions. So my basic message here is with a kind of weak restoring, 40 watts per meter square, let's say 1 month or 2 months. I mean, 2 months is 40 watts, but 80 watts per meter square is fine too. We don't affect too much the physics between the ocean, the relationship between the ocean and the atmosphere. But with very strong restoring, we affect it, and we also change the mean state of the circulation of the ocean, and this leads to a spin up of the model. And then we don't know if the signal we are going to analyze corresponds to the spin-up of the model, which is due to the very artificial restoring, or to the real phasing of the anomalies we want to. So that's very quick for the Pacific pacemaker experiment. So I did exactly the same thing. So you recognize the two first EUF of the SST, the time series at the bottom, the correlation between the pacemaker experiments and the observation is very high in whatever the restoring. This is the internal variability, so it's really very well constrained. So the SST is very much constrained, but now what I'm showing here is the difference of the mean over these 20 years between the pacemaker run and the historical simulation, the difference in temperature. So this is a zonal, here this is between 2 degrees north and 2 degrees south from the surface to 700 meters, and from Australia to South America here. This is a thermocline. So what you see, I mean, introducing a flux correction, I mean, a flux restoring over the eastern part of the Pacific, you change a little bit the mean state of the ocean with less heat stored here where the thermocline is, so meaning that it's going a little bit upwards. And then if you see the evolution of this change with the restoring parameter, then the stronger the restoring parameter is, the biggest difference you get. And for this one here, after a while, I mean, it's 2 days restoring, a very spurious effect up starting here, and the model doesn't do a really good job if you look at it.
Am I reading this correctly? You're actually only getting surface cooling in the most heavily restored case?
Yes, we get surface cooling here, and in the other case, you get surface warming here. And if you look at the currents, so this is the zonal current. So in weak restoring, you get an increase. So this is, I'm sure you don't see the dash pattern here, which corresponds to easterly current. So there is an increase of the current here, and this change is growing, is getting stronger and stronger with the restoring, and the opposite is happening for this one here. So, and the change here is significant. It's about 25% in that case, and in the upper ocean. And for the countercurrent here, the undercurrent here is about 15 to 20%. So it's not minor, I would say. So this can change also. This is going to lead to some spin-up of your model, because the heat storage in the equatorial band will be different than the historical simulation, and then we start to propagate in the overrun. I'm going to skip this one. And my last one, maybe the least convincing, but just to show you that prescribing observed SST, restoring to observed SST can lead to some spurious effect in the model beyond some spin-up that you can introduce. This is here, each dot corresponds to 1 point of the Niño 3 region, Niño 3-4 region. So this is temperature anomalies here and the precipitation anomaly here. So when the temperature is cold, you get less precipitation, and the temperature is warm, then you have convection basically. So it is the same graph here, but I've computed the anomalies per decile. Yeah. So in black, this is observed the model without any constraint. In blue, weak constraint, and in red, strong constraint. So this shows you here that with a very strong constraint, the variance that you impose in the model is stronger than the one the model really has, basically. And this can trigger also some spurious effects in terms of teleconnection. Okay, so some conclusion, I would say, don't push the button too far for the restoring term. So to me, this is my personal view, this should be weak enough to respect the high frequency ocean-atmosphere relationship, which is about 2 to 3 weeks. Going back to literature, there are a lot of papers about this issue. like paper from Clara's, and also there's this paper here from Claude Franquignoul, where I estimate the surface heat flux feedbacks from the different observed product. And so 40 watt per meter square is about the value that you get over the North Atlantic Ocean. You can get a little bit more here, up to 60 to 80, but not too much. Okay, thank you.
Thank you very much. I'm not quite sure what the iceberg, but we like icebergs in Canada.
So just back to my question, the time series of the temperature seems to be pretty similar across all restoring cases, right?
Yes.
And yet these specific responses are very different. Do you want to talk a bit about that?
Yes. So basically, I don't have the plot here. What you want is over a long period, when you average the flux term put by the restoring, it should be 0. But because of non-linearities, it's not 0. And because of model biases, it's not 0. So at a certain point, you create artificial heat input for the ocean. And then the ocean responds to this artificial heat input by the circulation changes. So even if at the surface it's really correct, then the ocean sees because we are in a coupled system, the ocean sees the fluxes that you put in. So this can lead to some spurious effect, yeah. And all of what I've shown here might be really model dependent. This is just for our model.
So basic issue is model error, right? So if you're trying to impose something at the surface and the model systematic error doesn't jive with that, you're really going to start spinning things up. And
Yes.
that's the problem. So
That's
you want to try to have something weak enough, it's not going to give a shock, but you're still going to, no matter what you do, model systematic errors, you're still going to do some kind of.
Yeah, but the thing is, you want to minimize this effect, and I would say that weaker restoring allows smoother digestion of the model of what you put in. I mean, it can digest it the biases basically.
Very French point. Yeah, just to follow up on what Jerry was saying, I'm going to show some related tests we've been doing at PSL with perfect model study. So you don't have the model observation difference, and you have exactly the same type. And we've been a bit further in trying to reconstruct the AMOC just through surface nudging, and the results that Christophe presented hold down. And I mean, I think that fundamentally you have a difference between trying to impose a boundary condition for the atmosphere and a flux for the ocean. These are completely separate things. And I think there's been a lot of confusion in sort of the pacemaker community, and also the experience with the flux correction, when you're trying to change the mean of the ocean. Here, you're not trying to change the mean of the ocean, you're trying to put the ocean on
the right track.
On the right observed trajectory. It's very different. So I think we should be really careful how we do it. It's a very nice demonstration.
Noel first. Well, I guess I will comment partly related to this. I think you didn't really say exactly the objective of this experiment. I think we all sort of know about it, but it would be very good to have this precisely written before you design the experiment.
You did.
I did. The objective at the beginning.
Well, it's partly because I don't think, the ocean circulation change. Is that part of your objective? That's why I'm asking.
Sorry.
Are the ocean circulation change? Are you trying to capture the ocean circulation?
No, I just don't want to have the ocean circulation change.
Why do we want the restoring at all? Why don't we just do a partial coupled experiment which the atmosphere?
Well, there's change and change. Again, you don't want to change the mean, you want to change the ocean so it follows the observed variability.
Yeah. You want to constrain the ocean to follow the observed evolution.
So you can call that change if you like, but it's a different change.
I thought part of the goal of this is simply to understand the tropical Pacific and this global impacts, explain the global temperature changes and explain the changes in the North Atlantic sector, or whether the North Atlantic SST changes can do the same. Right?
I think I didn't get it. I can hear what you're saying. Speak louder, yeah.
I thought it was louder. It's just that I think if we you want the atmosphere to say we observed SSTs, right? Then why don't you run the model in which that region of the global model sees the observed SSTs? Then you don't interfere at all with the ocean circulation.
So more or less, you don't care about the circulation biases in the ocean. They're second order to having the
So
SST.
you're saying that you overwrite the SSTs?
No, you don't do it in a couple, just before the
So
atmosphere
have an
sees the
essay. Have an
atmosphere.
essay.
Yeah, right. Yeah, sure.
Yeah, we did that, but
Why don't you let
that's
just
what.
Okay, yeah.
I just have a nice response to this
It's
one.
always nice to have good discussion. Yeah, I recall some GFTL experiments where they just intervened and they gave the atmosphere the flux that the ocean SST would have produced if it were like the observations, and the ocean didn't got the response from the atmosphere. So you adjust the flux rather than the SST. There were some attempts like that to see the impact of extratropical SSTs on the atmosphere, assuming that you prescribe SST, something goes bad.
Yeah, I mean, this is what I was about to show here. I mean, this is the 2003 heat wave with very strong restoring. I've did one specific run for this 2003 heat wave. So I have 30 members since 30 years. So here, this is the SST for this 2003 heat wave over Europe. So warm SST here and cold SST, the observed anomalies are I restored very strongly with this two-day parameter, two-day restoring. And this is what you get for the, in terms of atmospheric response, in terms of precip. So basically, here over the Mediterranean Sea, you prescribe very warm SST, so it's like 3 standard deviation of the SST. And what the model do, it just goes into some precipitation there, just right above the SST anomalies. And in reality, this is just, we know that, I mean, 2003 was a heat wave and it's dry. So a very strong restoring at internal timescale can lead to a very spurious effect here. And you don't get this if you let the atmosphere, if you let the ocean atmosphere free with a timescale of about 2 months, because it's just adjusted.
Okay, his last question, unless we have a really burning question.
Quick comment. If I understand correctly here, your pacemaker experiment, you're restoring the monthly value, and it's the internal observability that you want to constrain, yes. Right? And I agree with you that the small, the long time restoring is best, but my concern is that if we do this pacemaker experiment for the AMV that has this longer time scale, I'm afraid that this 2 month you won't be able to keep the anomaly that you impose there. At least we found results that we actually are not able to constrain the model to keep the SST, and because of the damping that occur on this time scale.
With this plot, you can really see that the decadal change, you can keep the anomalies pretty well. Decadal change is very well respected. So, and it's true in summer and it's also true in winter. I mean, you have this change here. It might be very much model dependent, yeah, that's for sure.